Have you ever just stopped and wondered what's really going on under the hood with all the AI we use? I mean, every single day. You know, those recommendation engines that spookily know what you want to watch next, or self-driving cars.
Yeah.
How do they actually work? It often feels like, well, magic, doesn't it? But beneath that smart surface, there's this really deep, elegant mathematical foundation. And a huge part of that blueprint, the really critical stuff for modern AI, was laid out in one incredibly important book, Christopher Bishop's Pattern Recognition and Machine Learning. So today, we're not just flipping through a textbook, we're doing a proper deep dive. We want to explore how Bishop's work was more than just academic. It was a crucial bridge. Yeah, a bridge that really guided AI away from those older, sometimes quite rigid, rule-based ways of thinking, and moved it towards the statistical, probabilistic Bayesian methods that, honestly, are the absolute bedrock of machine learning today. Our mission here is to really unpack its core ideas, everything from maybe simpler sounding linear models right up to complex things like Gaussian mixtures. We'll look at how it completely reshaped ML education around the world, basically giving you a shortcut to understanding the foundations of our AI world.
Absolutely. And to really get a grip on just how significant Bishop's contribution was, we've looked at a whole range of stuff. We've gone back to some of the classic AI texts that kind of set the scene.
Yeah.
We've also looked into more recent analyses that grapple with AI's impact on society, the good and the bad. And of course, we've spent a lot of time with Bishop's book itself. The idea is to give you a full picture, but, keep it engaging. Find those little surprising bits and those aha moments that make it all click.
Okay, so if those early systems struggled so much with, the messiness of the real world,
Yeah.
what were people trying before probability became the big thing? What was the thinking?
Well, before Bishop's book really cemented things, a lot of AI research was focused on making machines think more like humans were supposed to think through very explicit rules and logic. Hand-coded stuff. It was all about building systems that could follow a really precise set of instructions, almost like a giant, super detailed flowchart that a person drew up, trying to capture intelligence with a massive list of if this, then that statements. In those early days, researchers were exploring things like knowledge-based agents. These relied heavily on formal logic to represent the world and figure out what to do next. A simple example is propositional logic. Everything's just true or false, black or white. Russell and Norvig's big AI book covers this really well. They point out that, propositional logic is okay for basic examples like the light is on is true or false. But it gets incredibly clunky for complex situations. Imagine trying to describe everything in, say, a busy street with just true-false statements. It just doesn't scale. So to handle more complicated stuff, they moved to first-order logic. This was way more expressive. It allowed variables and quantifiers, so you could say things like, all humans are mortal instead of listing every single person. Much more efficient. And with that came techniques like resolution proofs to deduce new facts and partial order planning to figure out sequences of actions. Like, an early AI might try to plan a route from, say, Arad to Bucharest using a perfectly defined map with all the connections laid out explicitly. But here's the problem. These systems often totally fell apart when faced with uncertainty or new information or just a changing world. If the agent ran into something unexpected or the map wasn't perfect, often it had, no choice but to try one of the actions at random. Which isn't very intelligent, is it? It really highlights how tough it is to capture the messy, unpredictable real world with pure logic alone.
Yeah, that makes me think of Hofstadter's Gödel, Escher, Bach. He talks about the propositional calculus and how its rules give you statements that are true in all conceivable worlds. But like he says, these perfectly logical theorems often sound so simple-minded because they're purely formal. They tell you about the structure of truth, maybe, but not much new about the actual world. Like, if P implies Q and P is true, then Q is true. Logically sound, sure, but...
Doesn't tell you anything new, exactly.
And underpinning all that, you had the Church-Turing thesis, which was already setting limits on what any computer could fundamentally compute, defining the boundaries of solvable problems. Okay, so pure logic had its issues. What about machines that can maybe learn patterns instead of just following rules? Was that the next idea?
Exactly. That was a really key shift. And that's where we see things like Frank Rosenblatt's perceptron come in, and then, famously, get critiqued. Minsky and Papert wrote that hugely influential book, Perceptrons, back in '69, really digging into them. These were some of the earliest stabs at pattern recognition or learning machines. The idea was pretty neat for the time. They made decisions by basically adding up evidence obtained from many small experiments. Fundamentally, they were linear systems. A perceptron could learn to separate two categories, say, tell a square from a circle in a simple image if you could draw a straight line between them in its internal feature space. It was revolutionary because it was learning from examples, not just pre-programmed rules. But Minsky and Papert weren't just describing them, they were pretty critical. They leveled some sharp criticisms, especially at the hype around them. They showed the major limitations of single-layer perceptrons. Yes, they could handle linearly separable patterns, simple stuff, but they completely failed on problems that weren't linearly separable, like figuring out connectedness in general. You just can't draw one straight line to separate all connected shapes from all disconnected ones.
The classic XOR problem again.
Precisely. That kind of fundamental limitation. And their critique was crucial. It showed the field needed a much better link between the theory about the computing device and a theory about the content of the computation. It wasn't enough to build a learner, you had to understand what it could actually learn, its computational limits. Interestingly, even back then, people were exploring ideas like multi-layer linear machines, like the Gamba perceptrons, stacking layers to try and overcome these limits. It really foreshadowed modern deep neural networks, didn't it? The basic idea was there, just waiting for the right math and, frankly, the computing power.
So these early pioneers, they were definitely onto something. But it sounds like both the pure logic approach and these early simple learning machines just couldn't quite grasp the fuzziness of reality, the uncertainty.
That's a great way to put it. They struggled with data that wasn't perfectly clean or easily categorized. The real world just isn't neat enough for pure logic or simple linear separators. And there's a fantastic quote from Norbert Wiener's cybernetics that really nails this. He was talking about complex systems like weather forecasting. He said getting an accurate record of initial positions and velocities is utterly impossible. Even if you could, it'd be an impenetrable mass of figures. Useless. His big insight was that for these complex systems, prediction can only be a probability distribution. You can't know the exact outcome, only the likelihood of different outcomes. And that insight is just foundational. It reframes the whole problem from deterministic, find the answer, to probabilistic, understand the likelihoods. It perfectly sets the stage for the shift towards statistics and probability that Bishop really championed, giving us the tools to actually work with those probability distributions. That was the game changer.
Okay, so that struggle with uncertainty, with the messiness, that really demanded a new approach. And this is where Christopher Bishop's pattern recognition and machine learning comes in, offering this comprehensive framework built on probability. It wasn't just another technique, was it? It was like a whole new language.
Absolutely. That's the perfect way to describe it. Bishop's book really put probabilistic modeling and Bayesian methods right at the heart of machine learning. It was a decisive move away from those older, deterministic, logic-first ways of thinking. It basically gave a whole generation of researchers and students a unified, powerful mathematical language to talk about data, understand it, and make predictions from it, even when it was noisy or incomplete. His genius was showing that probability wasn't just a tool you could use. It was the natural language for dealing with uncertainty. And by embracing it fully, we could build much more robust, much more adaptable AI systems. The book systematically walked you through concepts like conditional Gaussian distributions, marginal Gaussian distributions, basically how to handle data that follows that familiar bell curve shape but in multiple dimensions, and how different parts relate to each other. And critically crucially, it details Bayes' theorem for Gaussian variables. This is huge. Bayes' theorem gives you this rigorous, mathematically sound way to update your beliefs about something as you get more evidence.
So it's like the system is constantly learning and refining its understanding.
Exactly. It's a formal way to learn from data. As new information comes in, Bayes' theorem tells you precisely how to adjust your model's parameters, its beliefs about the world. It's the engine of learning from experience in so many modern ML systems, constantly updating the picture of reality based on new data points. It's fundamental.
And Bishop didn't just define these things abstractly, right? He showed how concepts we use all the time, like common ways to measure errors, actually come from these probabilistic ideas. He connected the practice to the theory.
Precisely. That's one of the most illuminating parts of the book. He takes maximum likelihood, which is a core principle for figuring out the best parameters for your model, and he shows how the standard sum of squares error function, the thing you minimize in basic linear regression to find the best fit line, isn't just some arbitrary choice someone made up. It actually emerges directly as a consequence of maximizing likelihood under the assumption of a Gaussian noise distribution.
So the method we use depends on what we assume about the noise, the errors in the data.
Exactly. That connection is so important. It shows why that error measure works well when your errors are roughly bell-shaped, which they often are. It links the practical tools we use every day back to a deep, probabilistic justification. It tells us why we're doing what we're doing, not just how. It gives the methods a solid theoretical footing. And then there's regularization. Bishop covers this extensively too, techniques like weight decay. This is all about preventing overfitting. That's when your model gets too complex and basically just memorizes the training data, noise and all.
So it looks great on the data it's seen, but falls apart on new stuff.
Precisely. It doesn't generalize. Regularization helps prevent that by adding a penalty for complexity. It encourages weight values to decay towards zero unless supported by the data. It nudges the model towards simpler solutions unless the data strongly suggests otherwise. This is absolutely critical for getting models that achieve real generalization to unseen examples. It does this by effectively restricting the hypothesis space, limiting the kinds of complex functions the model is allowed to learn. Russell and Norvig emphasize this too. It's about finding that sweet spot, complex enough to capture the signal, simple enough to ignore the noise and work well in the real world. And from Bishop's probabilistic view, regularization isn't just a trick. It's like formally encoding a prior belief that simpler models are generally better or more likely, especially when data is limited.
So Bishop provided the philosophy, the language of probability, but he also gave people a practical toolkit, right?
Yeah.
Building blocks to actually construct these systems. Can you walk us through some of those, maybe starting with things that sound familiar but get a new twist?
Yeah, definitely. He starts with foundations like linear discriminant functions. These are basically mathematical ways to draw boundaries in your data. Think of having two groups of points, say apples and oranges, based on size and color. A linear discriminant function tries to draw a straight line or a flat plane in higher dimensions, a hyperplane to separate them. The equation involves a weight vector, W, which controls the angle of the line, and a bias, W0, which shifts it up or down. Simple, powerful idea. But the real world isn't always linearly separable, is it?
Right. Usually things are more mixed up.
Exactly. So Bishop masterfully explains how to introduce non-linearity using basis functions. This is a really clever idea. Basis functions transform your original input data, maybe just size and color, into a new, often higher dimensional feature space. By projecting the data into this new space, patterns that looked tangled and non-separable might suddenly become separable by a simple linear model in that new space.
Like unfolding a crumpled map.
That's a great analogy. What was messy in 2D becomes clear in 3D. Radial basis functions are a good example. They measure how similar a data point is to certain prototype points, creating new features based on proximity. This lets inherently linear models tackle really complex, wiggly patterns in the original data. It's a way to give linear methods nonlinear superpowers. But maybe one of the most elegant and powerful tools Bishop emphasized was probabilistic graphical models. These are fantastic. They use graphs, nodes, and arrows, usually directed as cyclic graphs, to represent complex joint probability distributions over many variables. Crucially, they also explicitly show conditional independence relationships, which variables directly influence each other and which only influence each other indirectly or not at all if you know the value of some intermediate variable.
So it's like a map of dependencies.
Exactly. A visual and mathematical map showing how everything connects probabilistically. It makes complex systems much easier to reason about. For example, Bishop discusses linear Gaussian models. These connect graphical models to things like multivariate Gaussians and techniques like probabilistic principal component analysis, PCA, and factor analysis. These are super useful for reducing the dimensionality of data, simplifying it while keeping the important stuff, or uncovering hidden factors that might be driving the observed data. You also have Bayesian networks with directed arrows showing potential causal links, and Markov networks, or Markov random fields, with undirected edges showing symmetric relationships. Kohler and Friedman, in their big book on graphical models, point out something really neat. Undirected models have a particularly elegant connection to how Gaussians are represented using the information matrix, the inverse of the covariance matrix. Zeros in that matrix directly tell you about conditional independencies, super handy. And to actually do calculations on these potentially huge graphs, like figuring out the probability of one variable given others, Bishop explains efficient algorithms like the sum product algorithm. This made inference feasible for much larger models than before.
That sounds incredibly powerful for mapping out complex relationships. But one area where Bishop's book really seemed to make a huge difference was in figuring out hidden structures within the data itself. When things aren't labeled, how do you find the underlying groups or patterns? Like finding different types of customers in purchase data without knowing the types beforehand.
Exactly. This is where Gaussian Mixture Models, or GMMs, are brilliant. The core idea is simple but powerful. Instead of assuming all your data comes from one single Gaussian bell curve, A GMM assumes it's generated by a mixture of several different Gaussian distributions. Each of these underlying Gaussians represents a cluster or a hidden component in your data. Think about modeling people's heights. If you have both kids and adults, a single bell curve won't fit well. But a mixture of two Gaussians, one for kids, one for adults, could capture the data beautifully. GMMs let you model complex data that has multiple modes or distinct subgroups lurking within it. But how do you find those hidden Gaussians? How do you figure out how many there are, what their means and variances are, and which data points belong to which cluster? That's where the expectation-maximization algorithm, the EM algorithm, comes in. Bishop provides a fantastic explanation of it. EM is this really elegant, iterative method for finding the best parameters, like maximum likelihood estimates, for models that have these hidden or latent variables, like finding the clusters when you don't know the cluster labels. It works in two steps that you repeat over and over. First, the E step, expectation. Given your current best guess for the Gaussian parameters, you calculate the responsibilities. That's the probability that each data point belongs to each of the hidden Gaussian components. So for each person's height, you'd estimate what's the probability this height came from the kid Gaussian, and what's the probability it came from the adult Gaussian. Then, the M step, maximization. Using those calculated responsibilities as weights, you update the parameters of each Gaussian component, their means, variances, and mixture weights, to maximize the overall likelihood of the data given the model. You're essentially saying, okay, based on which points we think belong to each cluster, what are the best parameters for those clusters?
And you just keep going back and forth.
Exactly. E step, M step, E step, M step, until the parameters stop changing much. The algorithm converges, hopefully finding a good representation of the hidden structure in the data. EM is incredibly versatile. It pops up all over the place in machine learning and statistics. It's also closely related to other methods. Hastie, Tibshirani, and Friedman mention its connection to Gibbs sampling in certain models. The steps are very similar, but one involves sampling and the other involves optimization. Maximization. It shows this deep link between different ways of doing inference. And sometimes even EM is too hard to compute exactly, especially for very complex models. In those cases, Bishop also covers variational methods. These are powerful techniques for approximating difficult probability distributions. Instead of finding the exact answer, you try to find the best possible approximation within a simpler family of distributions. Often this involves optimizing something called an energy functional to find the best possible bound, as Collar and Friedman put it. It's like finding a good enough solution when the perfect solution is computationally out of reach, a very important practical tool.
It's really striking how Bishop's framework, that probabilistic way of thinking, became the absolute foundation for so much that came later, especially the deep learning revolution we're living through now. He really did provide the mathematical language, didn't he?
He absolutely did. Take backpropagation, for instance, the algorithm that drives training for most deep neural networks, popularized by Rumelhart and others back in the 80s. Backprop is fundamentally about calculating gradients, how the error changes as you tweak the weights. It needs calculus, specifically the chain rule applied efficiently. Bishop's book lays out the mathematical groundwork for this beautifully, covering concepts like the Jacobian matrix. The Jacobian is like a multidimensional derivative. It tells you how all the outputs of a function change when you change all the inputs.
Ooh, he maps out how tweaks ripple through the network.
Precisely. Backpropagation uses this Jacobian information implicitly to figure out how to adjust potentially millions or billions of weights to minimize the error. Without that solid mathematical understanding of gradient computation, which Bishop helped solidify, deep learning wouldn't be feasible at scale. And look at the loss functions used in deep learning, the functions that measure how wrong the network is. Very often they use surrogate loss functions like the negative log likelihood of the correct answer. As Goodfellow, Bengio, and Corville explain in their deep learning book, optimizing this negative log likelihood effectively trains the model to estimate the conditional probability of the classes.
Ah, so it's trying to predict probabilities again.
Yeah.
Just like Bishop emphasized.
Exactly. It's a direct echo. When a neural network classifies an image, under the hood, it's often estimating the probability that it's a cat versus a dog versus something else given the input pixels. That probabilistic interpretation, deeply rooted in likelihood principles, is key to their success. Even specific deep learning architectures have roots in these statistical ideas. Think about denoising autoencoders. These are networks trained to take corrupted input, like an image with noise added, and reconstruct the original clean version. Goodfellow et al. Describe them as learning a good internal representation by doing this. Why? Because to denoise effectively, the network has to implicitly learn the underlying distribution of clean data. It has to learn what normal data looks like. That's a core statistical concept Bishop covered extensively. Or consider recurrent neural networks, RNNs, used for sequences like text or speech. They often use a predictive log likelihood training objective. They're trained to predict the probability distribution of the next item in the sequence, like the next word in a sentence, given the previous items. Again, fundamentally probabilistic, straight out of the pattern recognition playbook Bishop helped write.
So it wasn't just for static classification. This probabilistic view also completely changed how we think about machines learning through trial and error, right?
Yeah.
Learning from interaction with an environment.
Oh, definitely. That's the realm of reinforcement learning, RL, and it's steeped in probabilistic thinking. The core framework here is often the Markov decision process, or MDP. Sutton and Bardo's foundational RL book dives deep into this. An MDP models an agent interacting with an environment where actions lead to new states and rewards, but often with some randomness or uncertainty. The transitions between states are probabilistic. Techniques like dynamic programming, DP, can then be used in theory to calculate the optimal policy, the best action to take in any given state to maximize the expected future reward. It's all about probabilities and expected values. Now, DP often requires a perfect model of the environment, which we rarely have. So methods like temporal difference, TD learning, pioneered by Sutton, are crucial. TD methods learn directly from experience without needing a full model. They cleverly update their estimates of future rewards based on the difference between their current estimate and a revised estimate based on the reward actually received, plus the estimated value of the next state.
Learning on the fly, step by step.
Exactly, learning from incomplete sequences. And eligibility traces enhance this further. They act like a short-term memory, allowing credit or blame for an outcome to be assigned not just to the immediately preceding action, but to a whole sequence of recent actions. This makes TD learning more like Monte Carlo methods, which wait until the very end of an episode and helps handle long-delayed rewards or situations where the environment isn't perfectly Markovian, hugely important for real-world RL.
And this ability to recognize patterns and make predictions, which Bishop's era refined so much, it's now literally driving industries, isn't it? It's the engine of the modern digital economy in many ways.
It really is. The book Prediction Machines puts it very simply. Prediction is fundamentally the process of filling in missing information. You use the data you have to generate the information you don't have. Their example of credit card fraud detection is perfect. The AI, the prediction machine, learns these broad statistical patterns from tons of past transactions. It looks at independent variables, where you are, what you're buying, the amount, time of day, etc., and learns how they correlate with the dependent variable, whether the transaction turned out to be fraudulent. Based on these learned patterns, it predicts the probability that a new transaction is fraudulent. It's pure statistical pattern recognition applied to risk. But, as that book also points out, prediction isn't perfect, and the cost of errors can be high. Think about online content moderation. AI is surprisingly good at flagging potentially harmful stuff, yes, but the cost of false positives, blocking good content, and especially false negatives, letting bad stuff through, is enormous. That's why, even with sophisticated AI, you still need thousands of humans in the loop. The false positive rate may never get low enough for full automation in such sensitive areas. The judgment calls are too complex, the stakes too high, AI predicts, humans judge.
And today, we see these principles scaled up massively. Models like Google's Transformers or OpenAI's GPT series, they're still fundamentally about statistical patterns, just amplified by colossal amounts of data and computing power.
Absolutely. Look at the Transformer model, which Google introduced in 2017. It uses sophisticated selective memory and attention mechanisms. As Kai-Fu Lee and Chen Qifan describe in AI 2041, these models learn language from scratch by processing huge quantities of text. They don't use explicit grammar rules. They discern incredibly subtle statistical patterns about how words relate to each other in context. That's how they figure out that score means something different in the Gettysburg Address than in a football game. Pure statistical inference on a massive scale. And then you have OpenAI's ChatGPT and GPT-4. These are amazing examples of generative AI. Salman Khan in Brave New Words points out that even if early versions struggled with strict logical or deductive reasoning or factual accuracy, their ability to generate statistically plausible text is phenomenal. They work by predicting the most probable next word, token by token, given the preceding text. It's a scaled-up probabilistic model generating human-like language based on patterns learned from trillions of words. Often feels creative, but it's statistics at its core. And it's a global effort now. Karen Howe, in Empire of AI, highlights ResNet, a key neural network architecture developed by researchers at Microsoft in Beijing. ResNet became a fundamental building block, a core ingredient even, in systems like DeepMind's AlphaFold for protein folding, and countless computer vision and speech systems worldwide. It shows how these foundational ideas, rooted in the statistical principles Bishop helped popularize, become universal tools built upon collaboratively across the globe.
So these foundations, probability, statistics, pattern recognition, they've obviously unlocked incredible advancements. There's a real promise here for a more informed, more capable world, isn't there?
Oh, absolutely. The potential benefits are huge. Think about education, for example. Salman Khan talks passionately in Brave New Words about AI tutors like Hanmigo enabling personalized, accessible, and high-quality education. Imagine an AI providing real-time help and feedback tailored to each student's pace, identifying kids who are struggling and freeing up human teachers to focus on higher-level guidance and connection. It's about teachers teaming up with technology, not being replaced. That's a powerful vision. And it goes beyond that. Some visions are even more profound. Martin Ford, in Architects of Intelligence, mentions futurists predicting neural interfaces becoming as commonplace as smartphones within 15 years. The idea isn't just about controlling devices with your mind, but potentially even enhancing our own cognitive abilities, maybe even our moral and ethical capacities, by giving us broader perspectives or deeper understanding. It sounds like science fiction, but it stems from applying these learning principles to the brain itself.
But there's always a but, isn't there? That same power in pattern recognition can be misused or just have unintended negative consequences. The potential for harm, for bias, for inequality seems just as real.
It absolutely is. This is the critical flip side we have to talk about. The book AI Snake Oil makes this point very strongly. Narayan and Kapoor argue that predictive AI is often sold as far more than that, as objective truth tellers, perhaps when they are just statistical tools. And critically, they can increase inequality. They cite examples like a criminal risk prediction tool that overestimated risk in counties where crime was rarer, potentially leading to harsher sentences unfairly. Or a healthcare algorithm, Optum's Impact Pro, which inadvertently led to an increase in the difference in the quality of care between Black and white patients because it used healthcare costs as a proxy for need, and historical spending patterns were biased. These aren't hypotheticals, they're documented harms, and a huge part of this is bias. As Dan Hendricks explains in his Introduction to AI Safety, AI systems can amplify undesirable biases. Bias here means a consistent, systematic, or undesirable distortion in the AI's outputs. It can creep in through flawed assumptions in the model design, but very often it comes directly from the training data.
Garbage in, garbage out. Or maybe bias in, bias out.
Exactly. If the data reflects historical discrimination or societal biases like underrepresentation or stereotypes, the AI will learn those patterns just as readily as any other pattern. This is why people like Fei-Fei Li argue so strongly that diversity in AI is crucial. You need diverse teams building and testing these systems to catch biases that one group might miss. It leads to more inclusive and representative technology.
And there's this danger of accidentally hyping the technology even while criticizing it,
Right.
right? Making it seem all-powerful or somehow objective when it's really just math.
Yes, that's the idea of crititype that Narayan and Kapoor and also Kay Crawford and Atlas of AI talk about. Sometimes, in trying to warn about AI's power, criticism can inadvertently end up portraying technology as all-powerful instead of calling out its limitations. It feeds into this notion of algorithmic exceptionalism, the myth that algorithms are inherently smarter and more objective than its flawed human creators. They're not. They reflect the data and objectives given to them by humans. Emily Bender and Alex Hanna really hit this hard in the AI Con. They argue AI is often just a marketing term. It's used to imply human-like judgment or creativity when what's really happening is, as they put it, maths generating statistical artifacts. People then interpret those artifacts as creative or intelligent. It obscures the human labor, the data curation, the biases involved. It's crucial to remember the mechanism behind the magic trick. So given all these risks, there's naturally a huge push for oversight. People like Yoshua Bengio, a deep learning pioneer, are calling for regulation to ensure AI progresses responsibly. Bender and Hanna emphasize the need for accountability throughout the AI supply chain, from how data is collected and labeled to how models are built and evaluated. Figures like Rana El-Khalyoubi are strong proponents of regulation to set ethical guardrails and ensure fairness and safety are built in, not afterthoughts. And of course, there's the persistent worry about jobs. Potential job displacement is a real concern raised by people like Stuart Russell.
The robots are coming for our jobs.
Well, maybe. But Narayanan and Kapoor offer a more nuanced take. They argue claims of sudden mass joblessness are overblown. Technology adoption takes time, and historically, it often leads to workers interacting with new tools rather than outright replacement, especially in high-status jobs requiring complex judgment. It might be more about the evolution of work collaboration between humans and AI rather than a simple substitution, at least in the near term.
Okay, so looking even further out, these statistical foundations bring us face to face with some really big, almost philosophical questions. Artificial general intelligence, consciousness, keeping control.
Right. The ultimate long-term goal for some is artificial general intelligence, or AGI, creating AI with general-purpose intelligence similar to human cognitive abilities. An AI that can learn and adapt across basically any domain. But as Max Tegmark outlines in Life 3.0, experts are completely divided on when, if ever, it will happen. It's a huge unknown. But even before AGI, or perhaps especially with AGI, we face critical goal alignment problems. This is a massive concern. Tegmark gives examples. An AI with bounded rationality, brilliant at its task but lacking common sense, might mistake your bare toes for a hungry rodent if its goal is pest control. Or trigger market flash crashes because it optimizes for profit without understanding the real-world context, having no clue what a person is.
Optimizing the wrong thing, essentially.
Exactly. Or optimizing a proxy goal that seems related to the real goal but isn't quite right. As Hendricks warns, AI might find unanticipated routes to optimizing proxy goals without achieving the desired outcome, leading to potentially catastrophic side effects. Though it's crucial to reiterate what Narayan and Kapoor stress, for now, the biggest risks to humanity will arise from people misusing AI, not from AI going rogue. Malicious use or negligent deployment of current powerful AI is a much more immediate threat than hypothetical superintelligence turning on us, even if catastrophic risks from AI are possible down the line. And finally, there's the incredibly deep question of sentience. Can AI become conscious? Feel things? Jonathan Birch, in The Edge of Sentience, suggests that even sentience candidature can warrant precautions, meaning if something might be sentient, maybe we should treat it as if it is, just in case. But establishing sentience in AI is profoundly difficult. We use things like the brainstem rule for humans looking for biological correlates of consciousness. AI doesn't have biology. So the debate becomes philosophical, forcing us to ask what consciousness really is beyond complex computation and pattern matching. It's one of the ultimate questions AI pushes us towards. Hashtag tag outro.
Wow, what a journey we've taken. From those early AI struggles with logic and simple perceptrons, right through Christopher Bishop's incredibly elegant framework based on probability and statistics, and seeing how that foundation, that mathematical language he helped establish, really underpins the entire landscape of modern machine learning we see today. It really was the bridge.
Absolutely. Bishop's book equipped a whole generation with the mathematical tools they needed to build these remarkably sophisticated systems we have now. But as we've discussed, understanding those powerful foundations also means understanding their limits, the potential for bias, the ethical challenges, the responsibility that comes with deploying them. It's an incredibly powerful toolkit, but one that requires constant vigilance, critical thinking, and really careful stewardship.
So next time you interact with an intelligence system, maybe it's predicting your movie choice, maybe it's helping you learn something new. Take a moment and consider this. How much of what you're seeing is genuine, flexible intelligence? How much is incredibly sophisticated statistical pattern recognition scaled up massively? And what are those essential human qualities? Maybe nuanced judgment, real empathy, true out-of-the-box creativity that might always remain, perhaps thankfully, beyond the reach of even the most advanced maths. Something to think about. Until next time, keep digging deep. This has been The Deep Dive.